Hello, and thank you for joining Walrus Team 2, a group of extraordinary senior engineering students as we present our conceptual design, the Comfort Flow.
I'm Lisa Grove, the team lead.
I'm Chase Reeves, the prototype lead.
I'm Stanley Ha, the documentation lead.
I'm Joseph Bullock, the research lead.
I'm Stephen Philbrook, the design lead.
I'm Jacob Bemisturfer, the quality control lead, and we are Walrus Team 2.
Here at Walrus Team 2, our mission is to reduce the cost of cooling and increase comfort through the dynamic mixing of air. Central air conditioners do a poor job of evenly cooling a room, which can lead to a large uncomfortable temperature difference in a single room. While other fans can mix air, they do it inefficiently. Our product, the Comfort Flowbot, solves this problem by dynamically moving cooler air to warmer areas where it is needed most, resulting in even cooling throughout the room.
So who are the users and stakeholders for this product? Homeowners, renters, and even office staff can benefit from this design. The Comfort Flow primarily focuses on solving an issue which is prominent in warmer climates like the southern United States. However, its benefits are not limited only to this region. We designed our product to be used in any small to medium-sized room to maximize comfort and cooling efficiency. We conducted several initial consumer interviews to get a better understanding of the needs and pain points our customers might have. After speaking to Chad, Michael, and Andy, it became clear that hotspots were a significant issue in states such as California and Texas, specifically in places near windows or near exterior walls. The common pain point of these three potential customers was the frustration of having to adjust their vents and regularly reposition their fans. Because of this detail, we chose to focus on producing a fully autonomous system.
Our team had four main requirements for the Comfort Flowbot. Since the Comfort Flowbot will be used primarily in residential applications, it needs to have quiet operation, less than 60 decibels, which is about the same as a standard dehumidifier. It also needs to have efficient operation, providing at least 1.5 CFM of air per watt of electrical power used. It also must be able to achieve a uniform room temperature within 10 minutes of startup. This means that all points in the room will be within 2 degrees Fahrenheit of each other after 10 minutes. In order to effectively mix the room air, we need to be able to reach the warm spots. That is why the Comfort Flowbot must have a minimum throw distance of 15 feet.
All right, for our functional block diagram, we're going to have a microcontroller controlling the fan motor, the rotation, the vent fin direction, and the temperature sensor. Now, the rotation is going to be 360 degrees around in relation to the temperature sensor mapping out the room as it rotates. And this is all going to be done through air handling. Basically, it's going to grab air from the ground. It's going to move the air throughout the duct, and we're going to have the air exit through the vents. The airflow is going to go into the hot spots and cold spots of the room. In this case, it's just going to be hot spots for us for now. Now for our component block diagram, we're going to have 5 different sub-assemblies. One's going to be the control assembly, which is basically going to be the wall supplier, and it's going to go into a lot of buck converters to step down our DC from 24 DC volts into something that the device actually needs, such as the 7 to 12 DC volt for the microcontroller. Now, after the microcontroller, it's going to go to the actuation assembly and the temperature sensing. Now, for the temperature sensing, we're going to use IR sensors for the room mapping, and then we're going to also have temperature sensors for the inlet and outlet using thermocouplers, just to make sure there's nothing weird going on in our device. Now, for our actuation assembly, we're going to have a stepper motor, which is that 360-degree rotation that I was talking about, and we're going to have that servo for the vents fin direction up and down, and then we're also going to have that fan motor. Now, for the stepper motor and servo motor, we're going to go into the rotation mechanism where the stepper motor is going to go into a planetary gear drive to rotate it. And the servo is going to be also a gear drive, but it's just going to be a VIN vertical and lower movements. Now, for the air handling, as we've seen before, we're going to have that air intake from the ground. We're going to have that blower fan blow through the ducts, and then we're going to have that pivoting nozzle and rotation.
Here you can see the various major components of our CAD model. 3 major subsystems are the vent fin and post-fan ducting, consisting of the vent fins, vent and transition fitting, and servo motors. The rotation assembly consists of the gear drive mechanism and stepper motor. And the Arduino and thermal sensing system consists of the controller and sensors. That is not shown in this image since most of that is internal wiring. Here is a detailed view of the vent and fin assembly. You can see the servo motor on top will actuate the fins to the desired vertical angle using a link and inputs from the controller. This is a detailed view showing the gear drive mechanism. The stepper motor will receive inputs from the controller, which will drive the pinion, which in turn will drive the gear connector to the duct and rotate the upper housing and vent fin assembly to the desired horizontal angle.
For our uncertainties and unknowns, we are aware that there will be some losses due to the internal structure of our system, but as we're still working out the details of exactly what our internal parts of our system are, we can't calculate that quite yet. We also haven't taken the time to figure out what the maximum effective range limit is for our design. We know that it will be sufficient for a small room, but we don't know quite how far we can go with it. We also haven't tried to calculate exact cooling power or rate.
This slide summarizes the trade studies that drove our component selections for the Comfort Flowbot. For each of our 5 key components, we compared at least 2 to 3 realistic candidates using structured decision-making, weighing factors like performance, cost, size, and compatibility. For the IR temperature sensor, we selected the MLX 9614 ESF for its high accuracy and low costs. And prototype testing confirmed less than 1 degree of error against a reference temperature gun. For the vent blade servo, the MG996R was chosen for its compatible torque rating, and compact size, giving us enough margin to overcome airflow drag on the blades. For the system orientation motor, the SandMotion SF2424-10B11 delivered the highest torque, and it only costs about 1 amp per phase. For the fan, the 120 millimeter 24 volt DC fan was selected for its predictable band curve and 90 to 95 CFM output within our size and budget constraints. And finally, the vent blade will be 3D printed, and it should give us full control over the geometry and fit within our 8 by 3.5 inch outlet.
Here are our sample calculations for airspeed and pressure in mixed temperature. As you can see here, the pressure difference is not very large for the airspeed and pressure calculations, and the mixed temperature value is closer to the floor air that we are circulating throughout the room than the central room temperature. Now, the importance of these is that the first calculation shows we are not creating a significant pressure difference, which can cause resistance for the air moving in and out of our vent if the value is too large in either direction. So knowing that our value is rather small, losses from resistance should be pretty small as well. And for our second calculation, our mixed air temperature being closer to the floor temperature than the average room temperature before we started running our design, that's about what we want to see. So this validates that our design is operating successfully and as we would like it to.
This slide covers the key insights we gained from our proof of concept experiments across 3 subsystems. Starting with the airflow and ducting, we tested 2 duct sizes and found that the larger 4.7-inch duct significantly outperformed the original nozzle, extending our throw distance to 5 feet. However, this still falls short of what the final design requires, so a higher CFM fan has been selected. We also found that the vent fins reduced exit velocity by about 40 feet per minute, largely due to geometry and mounting offset issues that will be corrected in the final design. On the positive side, our 30-minute servo stress test passed with no wear or failure, confirming the servo mechanism is reliable. For system rotation, the stepper motor had no trouble rotating the system and even can handle additional load. The main issue was the gear drive was slightly too large to fit inside the housing, so a redesign is planned. Finally, for the IR sensing, the most critical finding was that the MLX sensor without the scope attachment showed a pretty high degree of error compared to our control, making it completely unsuitable for application. The long scope version, however, performed excellently with less than 1 degree of error across all distance of up to 96 inches. We also identified that these sensors require strict voltage regulation to avoid damage, which will be carefully managed in the final electronics build.
During prototyping, we tested 3 major subsystems. They were the vent fin assembly and post-fan ducting, the gear drive mechanism for rotating the outlet to the direction that we want it, and finally the Arduino and thermal sensing system. During testing of the vent fin assembly and post-fan ducting, we found that the fan did not produce velocity at the exit to produce the desired throw distance. The fan was incapable of delivering air to 7 feet from the vent exit. In order to fix this, we'll need to use a larger fan capable of delivering 1,730 cubic feet per minute. When testing the gear drive mechanism for the duct rotation, we found that the NEMA 17 stepper motor rated at 0.52 Newton meters of torque could rotate the assembly easily. The problem was the motor driver made the motor operate very loudly. In order to fix this problem, we will update the design to use a TB6600, which operates almost silently. The gear drive system also needs to be adjusted to allow for more precise, predictable control of the rotation. When testing the Arduino and thermal sensing system, we used a variety of sensors to test for accuracy at a variety of different distances. We found that the MLX sensor without a scope does not produce accurate results beyond 48 inches. In order to increase the accuracy, we will need to use an MLX sensor with a scope.
There are many moving parts. However, as development progresses, a fully integrated custom controller and dedicated power supply will provide the ease and use of manufacturability required for this type of product. Our design was optimized for a standard room size, no more than 16 feet in either direction, to be of most use to the everyday user. The body will initially be 3D printed until sales warrant the added cost of a molded construction.
For our comparison to benchmarks, we have a conventional tower fan as shown here. Both our design and the tower fan should shift the local air temperatures by a very small to almost negligible amount. Both will cause a small wind chill effect if they are directed at a user. The tower fan does cause noticeably more noise compared to our design, to the point that it might be very uncomfortable if it reaches 60 decibels. And the tower fan does move more CFM of air than our design does, but it would cause discomfort if targeted at a person, while ours should not. Our next comparison is to a home air vent / register, which should deliver around the same CFM as our design. The vent does send conditioned air into a room, which means it would have a significant cooling effect on the room, while our design does not. The cost, however, of installing a system like this, if you do not already have one, would be very high compared to ours, which would only be $100. And the noise decibel value for both designs will be around the same.
The bill of materials shows items purchased from Amazon for efficiency and low shipping prices. In this way, a single unit can be made for roughly $291. However, there is room to cut costs through bulk purchases and a combination of all the sub-circuit elements into a modern single controller circuit to reduce the number of parts and elements going into our design.
This slide outlines our fabrication plan for the Comfort Flowbot. The majority of our structural and mechanical components will be custom 3D printed and using a team member's printer. This includes the base stand, fan housing, exterior enclosure, internal ducting, vent fins, base gearing, sensor brackets, motor mounts, and shaft couplers. Printing these components ourselves gives us full control over geometry, tolerances, and fit, and this will allow us to iterate quickly as the design evolves. Our purchase off-the-shelf components include the NEMA 17 and Sand Motion stepper motors, the MG996R servo, and the fan, the IR sensor, and all electronics, including the Arduino stepper drives, servo motors, buck converters, and display. The key fabrication consideration going into the final build would involve maintaining a minimum duct diameter of 4.7 inches, confirming by our prototype testing, designing a permanent and precisely aligned servo mounts with the bump stop to prevent over rotation, redesigning the gear drive to fit the housing, and ensuring the strict voltage regulation.
After completing our prototype, we conducted 3 additional customer feedback interviews. The 3 individuals chosen to be interviewed were Chad, a homeowner and building manager who lives in California, Michael, a homeowner and smart device enthusiast who also lives in California, and John, a homeowner and retired HVAC technician who lives in Texas. On the right side, you can see the prototype images that were shown to these 3 interviewees. The exploded view is a CAD rendering of our prototype, and the other image is an internal view to the drive system that will rotate our device.
All right, and now for customer insight and feedback. We got a few things here. It's just make sure that the mechanisms aren't too noisy, has a speed control. A big one was text verification that it'd be more effective than a normal box fan on the market, which is definitely something that we would have to do next semester. This is probably the biggest concern from the customers. And in relation to that, at the bottom, you'll see that there are technical expert especially said we need to emphasize that the automation in the smart functionality is the key feature, and as well as to maybe add some convenience features such as a USB-C port since you lose that plug in your outlet.
Based off the customer's feedback we received, there's 3 main design changes we've chosen to make. Number 1 is using a larger and adjustable speed fan. Ensuring a higher CFM than the prototype will help increase comfortability and efficiency, as well as integrating a variable speed to maximize the cooling effect. The second is a temperature display integrated into the exterior of the device. Having a temperature sensor located in the intake of the device will allow the user to select the location in the room, which will be optimal for cooling. The third is integrating a USB charging port somewhere on the device. This will help users replace the lost outlet needed to plug in the Comfort Flow.
The FMEA shows our highest risk to be that of the controller, where its purpose is the bread and butter of our design. An inability to accurately locate a hotspot and output directional rotation and fan speed depends on many parts all working together seamlessly. From our original FMEA, this is a huge change. We originally were worried about dust limiting our fan throw distance, which due to the fan size and filters are no longer a concern. Motion of the system was another concern that was proven out through physical testing that we proved had a more than adequate power in our motors and controls. Room mapping using IR sensors containing a germanium lens improved the accuracy and ease of integrating the system into our controller.
And for our second semester Gantt chart, we're going to have quite a few things to do, obviously, but basically at the start, we're going to do a review of our current design, redesign a little bit, have a discussion on the final approval, and then we're going to have the manufacturing of the parts for quite a while, and then have that assembly for quite a while as well. And we're also going to do a bit of testing to make sure everything works correctly, redevelop and remanufacture, test everything again, maybe with the competition, review the data, and prepare for our final presentation.
For our lessons learned and surprises, we ended up significantly changing our original design idea from a register event interfacing machine to our current design, which is more similar to a tower fan. We learned about throw distance and its calculations, which most of our team members weren't really aware existed, and we didn't understand any of the math initially. We learned from customer interviews that people do not like air being directed at them, pretty much no matter what speed it is at. And we weren't initially aware that we could harness cooler floor air from lower in the room. We weren't aware that natural property of air was significant enough to actually utilize for our final design.
To summarize, the Comfort Flowbot addresses a real and common problem: uneven room temperature distribution caused by poor air mixing and single-point thermostat control. Our solution autonomously scans the room using IR sensors and redirects conditioned floor level air to detected hotspots with no user intervention required. Through trade studies, prototype testing, and 2 rounds of customer feedback, we validated our core concept and made meaningful design improvement, including upgrading to a higher CFM variable speed band, switching to a quieter stepper motor driver, and adding a USB Type-C charging port. based on user input. Looking ahead, next semester, our focus is on completing the gear drive design, finishing full system integration and validating our core requirement, getting any 2 points in the room within 2 degrees Fahrenheit of each other within 10 minutes of startup. We are also planning to develop a sleep mode for quiet nighttime operation and confirm noise compliance under full load. The long-term goal is to establish Comfort FloatBot as a smart, energy-efficient alternative to a standard tower fan, differentiated by an IR-guided precision and true automated room temperature uniformity.
From all of us at Walrus Team 2,
Thank you.
Thank you.
Thank you.